Well, what have I got cooked up for you today, guys? Look at it. It's solution of non-linear literal equations and simultaneous equations. My goodness. So fasten your seatbelts and get a nice cup of tea, maybe green tea, just to soothe you down, and we'll do this. Literal equations by hand. Sounds very grand. So we're going to solve those things. Oh, look. Oh, I reckon this is a snap, don't you? Here's A today. That looks like a nice little quadratic-y one, doesn't it? Yes, it is. So let's use a quadratic solution. And, yes, that's the general form of the quadratic formula, and that translates to this when you complete the square, as you're aware. And now we'll just put that into this sort of format here, and what do we get? Yes, we got A equals 1, B equals minus K, C is plus K, and we get that funny looking thing. And what is that going to do for us? Goodness. Yes, that looks alright, doesn't it? That's what X is. But of course there are some limitations to this little beastie under here, the discriminant. Okay, so we can't have a negative discriminant, can we? Otherwise, all bets are off and it doesn't work. There's no solution if the discriminant's negative. So therefore, we've got discriminant's k squared minus 4k, and that has to be basically greater than or equal to 0, because it can't be negative. Yeah? Alright, so let's see what we can do with that. Well, do you know how I do those? I basically draw a graph of the discriminant. Okay? And I do it like this. See that? That's basically the discriminant versus k. And that's the formula, right? K into k minus 4. So you want that to be greater than or equal to 0. You want the y value, if you like, or the whatever that thing is, a Greek capital delta, isn't it? Yes, you want that thing to be positive, right? On the vertical axis, right? You want it to be positive or 0, actually. You don't want it to be negative. So now, come on, which parts of k give rise to the parts of this graph that we want? That's the part that we want, isn't it? Yeah, okay, including these bits here where I'll put big green knobbly dots on them. They're the parts that we want. We don't want this part here at all, because that's where the discriminant's negative, and it just wrecks everything. So, because you can't have the square root of anything negative. That means no solutions, doesn't it? Yeah? So therefore, the part of the curve where delta is greater than or equal to 0 is shown in green, yes, and the k values which give rise to this part of the curve are shown in red. There they go. Yeah? Now, come on, you can just read them off now, can't you? Yes, so we can say that this is the solution of our literal equation, and we know that k is allowed to be anything from minus infinity up to and including 0. That's this sweep right up to there. And we also know that k could be starting at 4 and going up to positive infinity as well. So that gives rise to a properly specified solution to our little literal paradise equation, yeah? How did you like that? Well, I thought it was pretty good. Now, we better do B now. What's this thing? How are we going to do that? Well, I can see an x. I can take out x in common. That's going to probably save our life, I think. So, look at that, see? Now, that's really good, because in here now, we've got another quadratic, haven't we? And so, by the null factor law, x is going to be 0, or this thing's going to be 0, right? Oh, look at that! Goodness! Isn't that marvellous? Yes, this factorised really easily, didn't it? Of course it did. Yeah, just looking at that, yes. Yes, very good, excellent. So therefore, by our null factor law, we can say x equals 0, or x equals a, or x equals 4a today. I think that's about the end of that. Don't you think so? Great. Now, what was C again? That looks alright. What would you do with that? Come on, why don't you pause the video and have a go, and we'll see whether I agree with you, okay? Come back when you're ready. Here I am. How did you go? Well, let's have a look at it. So we know by the null factor law that x equals 0 from this one, right? This one. Or we know that this little beastie in here, in this bracket, has to be 0. So how do we solve that? Well, that's pretty... Oh, yeah, no problem. No problem. Yes, so you'll notice that I said here that b has to be greater than or equal to 0. Why did I say that? Well, you see, look, this you can't have a negative under a square root sign. So you've got to be a bit careful with that one. With these literal things, you probably need to be a bit careful with those kind of things. Like I was a bit careful with k in part A on the previous screen. Just as I was careful with k, you need to be a bit careful with b too, because if b was negative, you'd send this poor square root to hospital in a very bad condition, wouldn't you? He just couldn't handle it. They live on a diet exclusively of 0 and positives, yes? Okay, so that's the end of number C. What was D again? Oh, is that the end of that? All right. So solve the following equations for x now. This is a new lot. We've got ax cubed plus b equals c. X to the 3/5 equals k. I don't see any problem with that. X to the m over n equals a, where mn are natural numbers and a is a positive real number. That looks alright to me. And we've got these things here. Oh, look, we'll just do them in turn, shall we? Rather than get too overwhelmed with too much stuff here. So here's a. Alright, so what are we going to do with that, guys? Well, I think we subtract b from both sides and divide by a and then see what we get, don't you? Great. Well, wouldn't x just be, I think x is just the cube root of all that stuff on the right-hand side. Excellento. Yes? Pretty easy, eh? What about b? Right, so x to the 3/5 equals k. Oh, no problem. We'll just raise each power of that equation to the 5/3, won't we? Yeah, we will, and we get x equals k to the 5/3. For me, is an excellent result. Now, what about c? X to the m over n equals a. Oh, that seems very easy, doesn't it? Therefore, x would be a to the n over m, wouldn't it? Yes, it would. These are pretty easy. But, you know, they're testing your index law knowledge and all that kind of stuff, so they're useful. What about d? Well, I don't see a problem to you. So, therefore, x plus b to the 5 equals c over a. Therefore, x plus b would be the 5th root of that, wouldn't it? Yes, and then just subtract b from both sides, and we've got ourselves an answer. Thank you, Mr. Box. Well, that's excellento. What about e now? What about e? Yes, well, we could add a to both sides, and then we could divide both sides by 2, and then we could take the 5th root. Excellent. Well, this is going swimmingly, isn't it? Okay, what else have I got cooked up for you? Well, now this is simultaneous equations. This one here is actually a very nice little question, even if I do say so myself. We've got to find the values of p for which the graph of y equals px, in other words, going through the origin where p could vary, intersects with the curve of f of x equals x squared plus 1, never intersects in scenario A, or intersects once in B, or intersects twice in C. That's pretty interesting, isn't it? So let's just see if we can work with this. We've got y equals x squared plus 1, equation 1. We've got y equals px, equation 2. So guess what? We've got some simultaneous equations if they're going to intersect, yeah? Because the y's will be the same when they intersect, so let's make them the same. There we go. And we have to solve that now for x, and it's going to be in terms of p. Well, of course it is, isn't it? So there we go, using the quadratic solution as we know how to do. We get that, and we get that. Now, that's pretty fascinating. So the discriminant is the key, because we know, as we were discovering previously in this video, that the discriminant holds the key to whether you have no solutions, one solution, or two solutions. Yeah, you know that, don't you? Okay, so let's have a look at, we don't want any solutions in part A, don't we? So therefore, if you've got the discriminant is less than 0, you have no solution. So that means p squared minus 4 has to be less than 0 for that. If the discriminant equals 0, you get one solution. If the discriminant is greater than 0, you have two solutions. So this is the key to how to answer this question. Right. So let's draw a graph of the discriminant versus p. I always draw a graph because it tells me exactly what I want to know, okay? So there's the discriminant on the vertical axis here, and we've got p over there, and there's the graph of p squared minus 4, right? Y-intercept of 4, x or p-intercepts of plus and minus 2. So therefore, if we want the thing to be negative, that's where we want it down there, right? they are the negative values of discriminant, right? These are the positive values of the discriminant, and that's the zero value of the discriminant. So look, it's easy to work out now. Once you've got a picture, guys, it's worth 1,000 words in maths and in every other way as well in life. So now what have I written there? So when P is less than 2, in between -2 and +2, that's when the discriminant is negative. Can you see that? See, in here, these values of x give rise to this negative section of the curve, don't they? If you're not sure, just drop some vertical lines from the curve and see where they land on the x-axis, and you'll soon be convinced that I'm telling you the truth. Okay? So when P is plus or minus 2, that's when the discriminant is 0, which gives rise to one solution, doesn't it? Yeah? And when P is greater than 2 or less than -2, that's when the discriminant is positive. Just have a look on the graph if you're not sure, and you'll get yourself two solutions, right? That was pretty neat, wasn't it? So now I think I'm going to give you some graphs to show you. Now this is these situations are where you've got no solution. So these two lines here, I've given you y equals x and y equals -x. Now the gradients of those two lines both qualify for the no solution. Now what was the no solution again? It was basically P is somewhere between -2 and +2. So they both qualify, don't they? Yes? Okay? So if we were going from -1 up, well, I've got to be careful here. If you're going from -1 to -2, even though the gradient is getting more negative, this line is going up, right? Up, 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 up. Yes, that's more steeply negative, is what I'm saying. So everywhere from here down to a flat line, and anywhere from flat line up to here, or indeed right up to there, but not touching there, would get you no solution, right? Where P goes from -2 and up to +2, non-inclusive. I hope I explained that properly. I think I did reasonably well, yeah? Alright, so that's when P is between -2 and +2, and the discriminant is negative, so you get no solution. It's fascinating, isn't it? Isn't it fascinating? So here's our next case. Wow. Now this is where I've done you a P equals 2 and a P equals -2, and you'll see, much to your delight, guys and gals, that this does give you one solution, because this straight line through the origin, y equals px, in this case 2x, and in this case -2x, it grazes the quadratic graph at just one point. It's a tangent to it, so you get one solution. Isn't it magnificent? There's the case there, yeah? So, when P is plus or -2, you get discriminant is 0, and you get one solution. Yeah, don't you? Alright, so here you go. I know, you're gasping with wonderment, I know. Here's the last one. Now, this is when P was, now what was it? P was more than 2, here, right, this is 2.2x, you'll notice, and less than -2, that's -2.2x. Now, note that the number is more than 2, but it's because it's minus, it's less than a gradient of -2, right? Do you understand? Yes, the steeper it gets, the more negative it is, right over this side, yeah? Okay, so that's the situation there. When P is greater than 2 or P is less than -2, the discriminant is positive. You get two solutions. I just think this is just the most marvellous example to show you. You know, it's all literal stuff too, like y equals px, intersecting with that quadratic x squared plus 1. Do you like it? I think it's terrific. Now, what's this? The line with equation y equals -1/9 x plus 2/3, good heavens, intersects once with the curve with equation xy equals 1. Now, you think let's just demystify this. That's y equals 1 over x, right? Let's just call a spade here, guys. Not try to confuse everybody. Thank you. Now, we've got to find the equation of the other straight line with the same gradient, e.g. -1/9, which intersects only once with the curve. I see. That's very, very fascinating. Well, we can sort that out, can't we? We certainly can. So, the straight line required would have to have an equation of the type y equals -1/9 x plus some intercept, and that intercept wouldn't be 2/3 because that one's already taken. We're told that intersects with the curve in one spot. Yeah? Okay, so that's what we've got to do. So I think we've got a simultaneous equation, don't you? Yeah, I think we do, and then we can basically, once we work it out, we can solve it for k so that there's only one solution, right? Solving simultaneously, as we always do, make the y's the same. Solve it for x. Now you're going to multiply both sides by x to do this. This is why we're getting ourselves a quadratic. Quadratic is the superstar of all this stuff, isn't it? It just comes up everywhere. So, okay, so what is the discriminant? We want the discriminant, right? That would be for one solution, delta, the discriminant, would be naught. So let's work it out. That's what the discriminant is. And you get that funny looking thing. So therefore, what does that look like? 36 over 81. Well, that's a perfect square. Aren't you aware? And therefore, k would be plus or minus 6 over 9, wouldn't it? Plus or minus 6 over 9. Okay, so what does that mean? That's plus or minus 2/3 when you cancel that down. So y is minus 1/9 x plus 2/3, or y is minus 1/9 x, minus 1/9 of x minus 2/3. Now this is the one we got up here, already had. So basically, we don't want that one, although it popped out in our solution anyway. We want this one, don't we? Yes, I think we do. Absolutely. That was already given. This is the one we need. My goodness, we're on a roll here, guys. Look at this. What's this? So therefore, this one here, this one here is y is minus 1/9 of x minus 2/3, which cunningly intersects with this graph just once. And this is the one where y equals minus 1/9 x plus 2/3, which also intersects. Oh, I just reckon that's beautiful, don't you? And the graph, doesn't the graph just tell you everything? It just reinforces everything so beautifully. So, you know, this stuff's really quite fun, really. Oh, well, you know, it is fun. So, what do we got here now? Find the coordinates of the points of intersection of the circle with equation, that one. So that's got a centre of x is 4, y is 0, radius 4. With the line with equation y equals minus x plus 8. So there's no literals in this. I'm just giving you a straight simultaneous equation, right? So that's going to be fun. Come on, let's go. There's the equation 1's a circle, equation 2's a straight line. We've just got to solve them simultaneously, don't we? So probably we better substitute for, yes, for y from equation 2 into equation 1, okay? So how does that go? Yes, that looks all right, doesn't it? Yes, find the coordinates of the point of intersection. Yeah, okay, the points of intersection. So we've got to convert them into coordinates. Well, we'll solve it for x first, right? Multiply those things out. And yes, that's very nice, isn't it? The 16s cancel, and we get this stuff. Does it look right? I think it does. Yes. Cancel down by 2, and then factorise. Oh, look at this. A work of art. So therefore we can say that x is 8 or x is 4. They're the two x coordinates of the points of intersection, right? Now we just have to convert them into coordinates, don't we? So substitute x is 8 and x is 4 into the easier of the two equations, which would be equation 2. And we would get that, which would be a y coordinate of 0 when x is 8. And that's that. And then if x is 4, substituting that value in, we'll get plus 4. So that's the other point of intersection. So therefore the points of intersection are those two, and let's see. Oh, how wonderful. Look at that. So there's your, what's that? 4 and 4. This one's 8 and 0. Isn't it great? Look at it. It's pretty beautiful, really. So that's that. I think that might be the end. We were having such fun, weren't we, too? Yes, and you're a star, and huzzah, you'll go far, but you will need to practice. This literal stuff really does tend to do students' heads in. You've got to think about what you're doing. You really do, don't you? And look how prominent the quadratics were and the discriminants were. So you've really got to get used to these things. Use them. Practice them. Then all the little neurons and synapses in that beautiful brain of yours will connect properly, and there won't be any surprises anymore, and you'll be so good at it you'll surprise yourself. Okay, well, thanks again, and we'll see you next time. Okay, bye for now.